right, awesome. Hey everybody, thanks for coming out tonight. My name is Alex Pulowski, and I'm one of the co-organizers for the Knox Data Science group. Sweet. And so we're the data science meetup here in Knoxville, and try to be platform agnostic, covering many different things. In the past, we've done some things that are, different things related to Hadoop, Scala, all kinds of stuff. Tonight we're talking about Python library with Keras for neural nets, which is really cool. Knox Data Science, remember knoxdata.org? Yeah. So yeah, you can go to knoxdata.org. I haven't been very good at updating this, but anyway, this is kind of like our base site where you can find out more information about. I'm going to learn more. And so all the stuff that we do, our location, where we are. You want to click on the meetup. Obviously, most of you guys find us through the meetup page. So we actually have an upcoming one after this next month with Local Motors on their Ollie platform, which is the autonomous driving bus. We're going to have a presentation. I also run the Knox 3D printing group here in Knoxville. And so it's actually going to be a really cool meetup. We'll have an intersection of both the 3D printing stuff that they're using for Ollie, as well as the automated driving things that they're doing. That'll debut here in Knoxville this fall, which is going to be really cool. But before we get to that cool stuff, we got some really cool stuff tonight that Alex talked about with neural networks, stuff that I don't really understand, but he does, so it's really cool. Yeah, and so Knox Data Science, we're part of Knox Devs, which is an umbrella organization that's now been around for almost 2 years. And it started as a Slack channel with 5 people 2 years ago, and it's now 740 users, which is awesome. You can join us on Slack and see the conversations there. We have a data channel that's related to this group. So any cool things that you see, I highly encourage you to join Slack. So if you go to knoxdevs.com, you can hit the join Slack button, kind of guide you through and find the data channel and add that to it, and you start putting stuff up on there. So all kinds of stuff on there. There's a random channel that has amazing content every day. That's great. Not to mention the different custom emojis that we put in, as well as a rotating list of GIFs that happen. So it's pretty great. And then finally, I'm going to tech it up. This space that we're in tonight is Technology Cooperative. This space has been here about 6 to 7 years, and their main thing is, while they do some co-working during the day, there's some spots available here. Their main thing is they work with local kids in the area doing STEM-related activities after school. So they've done robotics type competitions in this space. They've done a lot of coding challenges, everything else. The Knox Python meetup happens every first Thursday here in this space. Data science, we're here every third Thursday. So every twice a month, there's a great meetup here. There's also a couple other meetups you can find on knoxdevs.com that also meet here as well that are super great. So yeah, this place is active. The best part about it is that Crafty Bastard's literally across the street. So it's probably where we'll head after this meetup. So stay tuned for that. Finally, so tonight I guaranteed all of you here that you would have a raffle for something. And so what it actually is getting started with data science, this book, making sense of data with analytics. So at the end, I will draw from that list of this great book. So one of you will go home with this. All right, I think I have enough time, so what I'm going to do, Alex, you want to go ahead?
Yeah, sure. All right, so my name is Alex Klibisz. I went to UT, graduated last December, and I'm interning at Oak Ridge National Lab now. And yeah, today I'll be talking about the Keras library for doing deep learning and working with neural networks in Python. Who here has used neural networks in any capacity? Cool. Play with them. Just playing with them more so, or
it's an introductory class.
Okay, introductory classes. Okay, cool. Yeah, so hopefully Keras will be. Who's used Keras? Maybe anybody? Nobody? TensorFlow? Anybody play with that? Okay, cool. So in my opinion, it's a little bit easier to use even than TensorFlow is. So hopefully at the end of the day, you'll have something to take away to go start working with some interesting projects on this kind of stuff. So just an overview of what I'll talk about, just a quick intro to neural networks so that you don't get lost in the rest of the concepts. Then an overview mostly of Keras, so how you structure networks, how you optimize how you do training, and how you can work with callbacks to do some cool stuff while you're training. And then a few more advanced features at the end. And then I've also got a slide with some learning resources, some stuff that I've gone through and found pretty useful. And at the end, if there's still time left, then I've got an example to kind of walk through with a real data set that I've gotten to work with. So yeah, so that should be it. So to start off with, neural networks as a model for doing things with data, the real motivation for a neural network is that you're able to model really highly dimensional data. So images, video, audio, text, pretty much things that are difficult to put in a spreadsheet and express as rows and columns in a spreadsheet format that's kind of where I draw the line for when a neural network becomes useful. And the really cool thing about it is that in most cases, the neural network can be used to learn to extract relevant features for you. So before, when people did image processing, they would do sort of hand-tuned features, extract things from the images based on their own heuristics. And the cool thing is that the neural network, you can now allow it to learn heuristics for you. So that's kind of the motivation. In general, you think of them as doing sort of layer-wise computations. So there's a set of layers starting with an input layer where your data goes in. And then it goes through a series of hidden layers that do different types of transformations to the data. Typically, it can all be boiled down to matrix multiplications of one form or another. And then there's output layers, or typically one layer where some relevant output comes out of the network for something that you're interested in. And the way that you train these things to come up with the outputs that you want is you typically give them a lot of data, and then you solve an optimization problem based on a function that you use to quantify how good the output is. So I'll go through an example here in a second. In general, when you're working with neural networks, another big thing you'll find is that having more data can help a lot. So they can be pretty sensitive in terms of how much data you're showing them and the quality of the data that you're showing them. So this is kind of the typical illustration of a neural network. On the left side, you'll have something like, so this is a digit from a really common data set that people look at called MNIST. And so it's a 28 by 28 image. When you unroll that, just to have the individual pixel values, 0 or 1, then you can unroll that into a 784 input layer. So that's what the neurons on the left side there are doing. So you've unrolled the image, and it's going in on the left side. And then it's getting processed by these hidden units, doing different types of transformations to it. And then on the right side, on each one of these nodes, you'll basically get a value between 0 and 1. Or sometimes you'll do it in such a way that all the values together add up to 1. So in this case, that's what this example is showing. So it's taking a 5 on the left side, and on the right side, it gives you sort of a probability distribution over what the input was. In this case, the 5th node has the highest value. So you would say that this digit is a 5. If this is kind of the model that you're using. So that's a pretty simple, just visual expression of what's going on. You've just got stuff coming in on the left side or on one side, doing computation through the hidden units, and then on the other side of it, you've got some way to interpret what that input was. In this case, it was just 10 nodes that will give you a value of how likely that particular value is. So some of the common terms that you'll hear, a layer is just, like I said, something that a computational unit that'll take inputs, and then it'll compute some sort of function on it and pass those outputs to the next layer. There's different types of layers that people talk about. Convolutional layers are typically used with images. The cool thing about them is that it's sort of like a sliding filter across the image, and so you learn the values in the filter in order to amplify certain features in the image as it gets passed on to the next layer. Max pooling layers you'll hear about, and those typically just take, they look at also sliding windows across the image, and they'll take the max value within each sliding window, and it's sort of like picking out what the maximum vote was for a certain group of inputs, and then passing that along as a signal to another set of layers. Dense layers typically occur at the end of a network, and those, so for example, in this network here, all of these are considered dense layers because each one of the units, like right here where my mouse is, each one of the units from the previous layer is getting input to this unit. And then you can do the same thing with this one. Each one of the units from the middle layer is getting input to it, and so on and so forth. So those are dense layers. You have a lot of connections in those. And then throughout the network, you'll have activations. Some people consider these to be activation layers, and what that basically means is it's taking a value and computing some sort of nonlinear function on it. So a common one is to just basically take the input value and clip it at 0 and then the value. So if the value is less than 0, it becomes 0, and if it's greater than 0, you just keep that value. So what these functions allow you to do is learn nonlinear relationships between your input data and your output data, which becomes pretty valuable in terms of how you're representing your data and then doing classification on it later. So when you hear parameters, that means that each one of these nodes in the network has a weight that it's using to compute to compute a function on its input. And so what the network does over time, what your optimization function does over time, is it tunes these parameters so that they're doing so that they're approximating the output that you want more and more closely over time. And then the cost function, you'll hear about the cost or the loss or the objective function. This basically takes the output that should have come out of your network and compares it to the output that did come out of your network and quantifies how far apart those are in some sense. And that's what the optimizer uses to basically minimize that cost. So you want that cost to keep going closer and closer to 0 as your network trains. So while you're training, you're basically updating the parameters, like I had here, just the parameters, you're updating those to minimize the cost. So you want that cost function to go down. Another term, batch, that you'll hear, so that's basically a subset of the training data that you're using to train your model. You show it to the network all in one pass. All the data goes through. You compute your outputs and your losses, and then you update all of the parameters based on those losses, that data. And sort of the reason you do this is because a lot of times you can't keep all of your training data in memory, and so you're updating all the parameters in your model just with one sort of representative batch of the entire set of data. An epoch is sort of a semantic term, more so than having a concrete meaning. It means basically one pass through all of the training data. So however many batches it takes to go through all of your training samples, that'll typically be referred to as an epoch. So all these words. But in general, you can think of a neural network as being trained like this. So as long as your loss is above 0, you're going to call the network with some input data, that's X right here. And along with the weights, it's going to determine an output. And so that's your Y predicted value. And then you compute your loss based on, for example, just subtracting the predicted output from the correct output and squaring it. So that's one common loss function. So in the example that I showed before, you know, for the 5, the correct output would be all zeros except for a 1 at the fifth index, right? So then you would take this vector that came out of the network and compute the loss between the correct one, which is all zeros except for 1, 1, and this one, which was mostly confident that it was a 5, but maybe it was an 8, right? Because you had the 0.2 there. So this wouldn't quite minimize your loss, but it's better than having, you know, even values all the way across. And so then once you've computed your loss, you use that loss to optimize your weights and get a new set of weights. And you just keep basically updating these weights. I used weights and parameters, it's the same thing. You keep updating these weights until your loss has hit 0. So until for every time you showed a 5, it's outputting all zeros except for the 1 at the 5 index. So that's kind of the heuristic way of, or the high level way of thinking about how these things are trained. So I'll show a quick example in the browser here. So this is one that you can actually go, and it's a neural network being trained in the browser for the image classification task, the digits classification task. So you can see over time as it's training, the loss is decreasing, which means it's getting more and more correct over time, or less wrong, I guess, if you want to put it that way. And you can pause it, and you can see that at this instance, the classification loss was around 0.18, so it's getting pretty good at this point. You can look here and see the different types of filters the different types of layers that they're using for the network. So in this case, they've got an input layer, a convolutional layer, which is basically a bunch of filters sliding across the image and computing some sort of output off of it. A pooling, which cuts the dimensionality in half, so it just gets rid of the data and keeps around the strongest signals. And then another set of convolution and pooling. You'll see those in pairs a lot of the time. And at the end they've got a softmax output. So what the softmax output does is it makes it to where all of the nodes at the end of the network, the vector that they output, those values will add up to 1. So it's sort of a distribution over what the most likely value is given your input. And so you can actually go through here and scroll down and see that the convolutional filter, whenever the convolutional layer, when it's got 8 filters, and so each one of the filters in the convolutional layer is computing one of these outputs. And then that output gets passed along to an activation layer. And so this is what it looks like after it's gone through the activation layer. And then, like I said, you cut the dimensions, you cut the height and the width in half, so the output gets smaller, in this case right here. And you keep repeating this until at the end, what was the image that it got shown? I guess that could be a 1, you could say. You get all the way to the end, and you'll see the brighter the activation, the higher the value in this case. So if I zoom in, so you've got your output activation for 0, and then your output activation for 1, and you'll notice that the activation for 1 is the greatest in this case. So the network is predicting a 1 in this case, and that's yeah. So that's what you on the last layer is that it was a 1, and all the other values are zeroed out. So that's kind of at a high level how these things work, and you guys, you can go in here and play with this library. It's a little JavaScript library that lets you run some really simple neural networks in the browser. So I guess I'll link the slides at some point on Meetup. Yeah. All right, so just to review one more time, make sure nobody's lost. You're throwing data at it on the left side. It's computing some crazy stuff that's really specific to the problem typically. That's what you get into once you start learning about it. And at the end, you're outputting something that should come close to a correct value. And over time, you're evaluating how well it did and minimizing the error. So now I'll start talking about the library a little bit, Keras. So Keras is a Python library that gives you abstractions for layers, cost functions, activations, different types of optimization for neural networks. And so it really runs the gamut in terms of the different types of layers that it implements, and the different types of optimizers it implements are all pretty much state-of-the-art from the literature up to date. So that's really nice. The abstraction level is similar to scikit-learn, if any of you have used that. So it's basically define your data, give the data to the model, and call fit on the model, and it'll, whatever optimizer you used, it'll use that optimizer to minimize the cost for you. So a lot of that stuff, it basically rules out all of the calculus that you'd have to know to kind of implement this stuff on your own, which really isn't that much when you start doing it, but it simplifies things a lot. And then Keras by itself is just a front end, actually, to other libraries. So as a back end, you can use TensorFlow or Theano, or now you can use CNTK, which is a toolkit from Microsoft. So if you've done TensorFlow in general, it's not much, but it's definitely lower level than Keras. You can have a little bit more control over what you're doing, but it takes a little bit more code to do the same thing. So it's always a trade-off. But yeah, so that's a quick overview. Use it, and these are my opinions. It's written in Python, so if you're already familiar with Python, that's a good thing to get started with. It has R bindings as well, so if you've only ever used R, you can get by as well. In general, I'll show you kind of how the networks look. I find that it gives you really clean abstractions in terms of talking about the different types of layers that you want, and just basically sticking them together and then training your model to see how well it does. And what this allows you to do is prototype really quickly. So it allows you to try out different configurations of networks, different training configurations, without having to basically rewrite a lot of code. So that's a nice thing for sure. It does GPU and CPU support out of the box. So GPU support for neural networks is a huge thing. There's a lot of things that can be parallelized with the neural network. And because you're doing so many matrix computations, the GPU really helps out doing training for neural networks. So that's a really nice thing to have out of the box. It'd be a pain to implement on your own. And the reason it does that is because it has TensorFlow and Theano and CNTK as the backends, which are actually talking to the GPU. Compared to other libraries, I've found the documentation is also really thorough, compared to some of the other libraries. If you go look at the documentation, you'll find over here on the left side, you've got basically any type of layer that I've ever wanted to try to use. So You've got 2D convolutions, 1D convolutions, different types of recurrent layers if you're wanting to work with recurrent neural networks, which are a whole other topic. So yeah, so it does a really good job of implementing it in a way that has all the latest stuff, basically, and documented really well. And then there's also example scripts. So there's about 24 examples, a lot of which are coming straight from the literature, from the most recent things that people are doing with neural networks, and implementing it with the layers and the different configurations in Keras. So yeah, that's kind of the last point. It's really easy to go and get started working with a state-of-the-art network. You know, whether it'll work well out of the box is another story, but you can at least get some good footing and get started on it. So this is kind of how the network structure looks for a model in Keras. So what you'll do is define that you want a sequential model. So you've got your layers going basically from left to right. At the first layer, you want a 2D convolution, which is similar to what the MNIST, the digits example had in the browser. And then you tell it you want another 2D convolution, this time with more filters. Then you tell it you want max pooling, and you want dropout. Dropout is basically it'll randomly drop inputs from the previous layer. And what that does is it makes your model more robust to different types of data. So it basically prevents your model from overfitting on the data that you're shown. And then at the end, similar to the model we had before, it's got a dense layer with 10 nodes and a softmax activation. And with all this, you basically got a model that will get to 99% accuracy on MNIST without really having to do anything except name the model you want and give it a parameter for how many filters you want in it. So that's a really nice thing that you can just go through and set this up with some really simple Python code. So then when you want to before you train your model, you compile it in Keras. And when you compile it, you define what optimizer you're using and what loss function you want to minimize. So in this case, you're telling it that you want to minimize the mean squared error loss function, which is just the true vector minus the predicted vector, and square it and then take the mean of that. And then you can tell it that while it's training, you want to be able to see the accuracy metric, right? So while you're training, you kind of want to know how accurate is this thing getting. And so you'll define an accuracy metric for it. And then you'll take the optimizer, and the optimizer parameter basically takes an instance of whatever type of optimizer you want to use to train the network. So you've got pretty much everything that's come out in the literature until, I don't know, maybe they don't have stuff that's like a few months old, but they've got stuff from all the way like to 2015, 2016, new optimizers that have come out, and they've implemented them in Keras. So that's a really nice thing that you can pick from different types of optimizers. And so then when you train it, similar, like I said, to scikit-learn, you'll just call .fit and you'll give it your training data. So your inputs are your X and your outputs are your Y. So you give it the training data, you tell it how large the batch is. Again, that's how many examples it's being shown in between parameter updates. How long you want it to train as the number of epochs. And then you can also do validation, right? So you can take a set of data that you're not training on, and then after each epoch, it'll validate for you and tell you how well you're doing, so you can make sure you're not just overfitting on the data you're training on. So when you train, it looks kind of like the output here. Let's see if I can log into the computer I've got at home. So this is just the example that I showed you with the handwritten digits. It's called MNIST again, and you can just download this MNIST example from the Keras repository. And then it'll go through and it shows what backend you're using. And then it'll show you, you can really easily get it to show you a summary of the layers that you're using in your network. And then over time, it'll show the training loss. So you see the loss is decreasing in general, so it's doing a good job of learning to identify the digits correctly. So you see the loss that you defined, and then the accuracy that you wanted to see, and your validation loss and your validation accuracy right here. So it's a pretty good interface in terms of just, all this stuff, all this nice progress bar and all this kind of fancy stuff is implemented for you just within that fit method that you call. So that's just an example of what it looks like when you're actually training. So while you're training, a lot of times you want to, for example, save the weights whenever your network is improved, or you want to maybe execute some sort of function to do some more complex validation, more complex than Keras can do by itself. And so a good way to do that with Keras that's built in is this idea of a callback. And so basically what a callback is, it's a function that gets executed either before or after training, before or after an individual epoch, or before or after an individual batch. So say, for example, that I wanted to take those metrics that were on the screen there and I want to save them to a CSV file. Keras has a built-in callback that you call. You just instantiate this class CSV logger, and you tell it where you want to save your metrics to. And after every epoch, it'll go in and save those metrics. It has all sorts of really useful callbacks that you can use. For example, one that I commonly use is that when you're training and your model stops increasing, a lot of times a good idea is to decrease the learning rate, which is a parameter to the optimizer. And so you can set it, there's just a built-in function that you call, you instantiate it as a callback, and you tell it that whenever my validation loss hasn't decreased in 5 epochs, decrease the learning rate by such and such amount. And that basically makes it to where your model can, you can just let it run and it'll monitor, how long has it been since I've improved? If I haven't improved, let's tweak a parameter, and then start over. And so, yeah, go ahead.
I'm just new to CNX. So is there a way to specify how many hidden layers to use?
Yeah, definitely. So really in principle, all of these are hidden layers, right? Each one of these is its own layer. And so, yeah, I could add like, I could even do like a for loop and add 50 conv2d layers if I wanted to. Yeah, so you can, so that's where you don't explicitly say like, 10 hidden layers and then go train. You add each one of them, and that's what ends up being the number of hidden layers. Yeah. Okay, so yeah, the point with callbacks is a lot of times you want to execute just arbitrary code while your network is training to do different types of checkpointing or monitoring progress in different ways. And using callbacks that you just pass to the fit method is a really convenient way of doing that, I've found. So yeah, so that's another cool feature that it has just built in out of the box. So some of the more advanced features that once you start using Keras for a while, you'll find yourself going towards. This first one is called the functional API. So I guess with the way that they draw the line is the sequential API, the one that I showed before, is called sort of the object-oriented API, and then this one is called the functional API. And what it allows you to do is basically set up individual layers as a variable. So for example, you've got your input layer there. You've got typically they'll just call it X just for brevity. And you say X is a dense layer with 64 neurons in it that does a ReLU activation, and it takes the input layer as input. And then you'll do the same thing for the next one and tell it to take the X layer as input, so the previous layer that you did above. At the end, you put it all together just by instantiating this model object that you tell it what your input and your output layers are. So that's another way to create a network. The reason that this becomes useful is for models like this one. So this is a model that came out of, I'm pretty sure it came out of Google maybe a little bit less than a couple years ago, and it did really well on this is a particular subset of the model, but it did really well on image classification. And you'll notice that the input layer here at the bottom, it's actually feeding into multiple different layers. And so you can't set that up with the sequential API, but you can with the functional API. So what you could actually do is say like this model, the one on the far left is taking X as input, and this one is also taking X as input, and this one, and then it do another loop around right here. So it gives you more flexibility to set up kind of crazier architectures. So you're not really constrained to things that just go one pass through. So that's a really cool feature, because nowadays when you look at the literature, you'll rarely see just a simple like one pass-through neural network. People are figuring out different sorts of non-trivial architectures that work well for certain problems. And when you use Keras, you're not constrained to using just the simpler architectures. So another thing that's neat about the the functional API is that it lets you do multi-input and multi-output models. So an example of when you might want multiple inputs is if you have, for example, if you have, for example, in your training an image, and then you also have a caption for that image. So you could set up a model that takes two inputs, one being the image, another being the caption, and at the end it outputs another caption, for example, or something like that. So this is just a diagram of that sort of a model. You can see that in this case it's only taking one input, but then it's got two outputs right around. So the first one comes out right here, the second one comes out right there. And the really neat thing is that you can actually compute two different loss functions against each one of these outputs, which is just another really cool way that Keras allows you to be flexible in terms of how you implement your architecture. And the final advanced feature that I like to use a lot, whenever you're working with a lot of data, like probably on the order of gigabytes or tens of gigabytes, it becomes impractical to load all that into memory. Even if you do have all that memory available, it's slowed on the front end to load it in and do your training. So what Keras allows you to do is, instead of calling just the fit method, it has a fit generator method, and you actually give this method, you give it a generator. And in Python, a generator is basically a function that you call. You take the generator and you call next on it, and it outputs another set of outputs. And then it doesn't do anything, and then you call next on it again, and it outputs another set of outputs. But it maintains state within. So what you can do, for example, is if you have a huge directory of images, you can load in maybe the first 50 images into your generator and pass them out to the network, and then wait till you get called again, and then it'll load in the next 50 and pass them out to the network. And so yeah, so it's really nice for anytime you want to work with a non-trivial size data set, or you want to do, for example, different types of augmentation to your data while you're training, then just defining the generator and then passing it to this fit generator method is the way to go for that kind of a setup. So yeah, that was Keras and neural networks, I guess, real briefly. The last thing I've got here, unless we want to take more time afterwards, is a set of learning resources. So I've ordered them kind of from how simple they are to how difficult they are to learn from. The first one is Data Skeptic. It's a podcast, and what I really like about the podcast is they have kind of two classes of episodes. They have one episode where they'll do an interview with somebody from either industry or that's doing research on different machine learning topics, and they'll go super in depth in it. And then he actually has another episode where another type of episode called mini episodes, where he'll take a certain concept and dissect it using really assuming no prior machine learning knowledge. So he'll use different types of examples from real life about how these concepts can be kind of mapped from things you already know to how they're actually working and why they're good for machine learning. So it's a really good resource. Machine Learning Mastery is a website. It's kind of a blog, and he also sells ebooks. I really like the ebooks that he puts out. So he's big on kind of like forget the theory and just learn the code kind of approach, which is nice if you're not comfortable with the theory. It only goes so far, but it's really good for getting started. So he has several books that I've gone through. Let's see which one would I recommend. Definitely Machine Learning Mastery with Python is a really good one. He goes through and basically teaches you the entire scikit-learn library with very practical examples, like here's the code, here's what it's doing, now go code it up on your own. Doesn't really get much into theory. And then he does the same thing for deep learning and neural networks, and now he's recently done some on time series and on XGBoost, which is another algorithm that's gotten pretty popular lately. So yeah, they cost a little bit, but I thought it was worth it to buy these and go through them. Similar PyImage search, he also blogs and has some ebook products. It's pretty similar, but this one is more specific to image processing and working with models that are doing stuff on images. Another really good resource if you've got like 2 or 3 days that you're bored and you want to just dig into something really kind of non-trivial is this book called Neural Networks and Deep Learning. And it looks kind of simplistic when you first look at it, but he goes into really good detail about how you would implement a neural network with the motivation of doing handwritten digit recognition. So at the first he starts kind of describing what the different types of neurons are and what functions they're computing. And then he gets all the way into proving why a neural network can approximate any function. So that's a really good in-depth set of chapters basically to go into. And it'll take you, I don't know, unless you're really familiar with this stuff already, it'll take you probably a week or two to get all the way through that. And then the Stanford CS231 course is a really good course, mostly on also computer vision with deep neural networks. You can watch the lectures on YouTube, but I found that you get more out of actually trying to do the assignments because they're pretty challenging, and they'll push you. But you can also typically Google it and find solutions out there on the internet if you get stuck. So that's a nice one. And then the deep learning book, very generic name, but it's a book put together and it's online for free, and it's by 3 guys. This guy is a little bit younger. I think he just finished his PhD, but he's done a lot of really good work in machine learning. And then the other 2 as well. Yoshua Bengio is a professor who's been around for a while, but he's kind of a legend in the area. So if you really want to push yourself with like the theory and all the details, then that's a good one. And then if you just need a good math review, basically like you need to be familiar. If you want to go beyond a certain point in machine learning, you'll start looking at like different types of matrix operations, if not just to make them faster, and then also a little bit of calculus. And so I found that this book, Math for Political and Social Research, is actually a really good kind of dumbed down version of what you'd get in a regular math book. So that helps if you haven't seen derivatives or things like that in a couple of years. So are we constrained on time, or do we have like 5 more minutes? Okay, cool. So this is just an example project that I've done just to kind of learn. And the project revolves around this data set, which is, let's see once it loads. So it's images from within cells, and you basically want to figure out where the boundaries are between these certain elements in cells. And so you have ground truth masks. For example, the mask for the one right here on the left is the corresponding one on the right. So it tells you where the different parts of the cells are, basically foreground or background. And you want to use a neural network to compute, to take this image on the left as input, and then compute this output and learn to do this output from the input. So that's what the problem revolves around. The architecture the neural network architecture that came out a few years ago, 2015, that is designed for this kind of a problem is called UNet. And so what I did is you go and read the paper, you go and Google this stuff and you read the paper and you see a diagram of the architecture. And this is what it looks like. So basically, I'll put out trip on the table. You're taking a tile from your image as input right here, and then you're doing 2 convolutions across the image, and then you're doing a pooling step. So it's cutting the image dimension in a fourth. So it goes down here, and then it does the same thing, a couple pooling layers, or a couple of convolutional layers, a pooling step, and it goes down here. But the cool part about it is that you're actually taking the output that comes out of this layer, and you're passing it over to this layer. And so you're doing the same thing also for right here to right there. And what ends up happening is that this downward pass basically gets your image to a really small size. So it's actually at the bottom here, it's like a 32 by 32 image once you've started with like a 570 by 570. And then these layers on the right side, they restore the original size of the image, but instead of recomputing the image, they're computing that output mask. And the layers, the sort of, these are called skip connections in between. People have found, and they've shown kind of the theory behind why those help a lot with this kind of task where you're just learning a mask of an input image. And so implementing this by hand, you probably don't want to try to do that by hand, meaning just like with Python or with CUDA or something like that. It would take me probably like half a year to do it. So the cool thing is that with Keras, you can put together this kind of a complex architecture pretty easily. So what I've done here in the first layer, you give your layers names so you can keep track of them. So you've got convolution layers, an activation layer, another convolution, another activation, and then a max pooling. And so once you've saved this conv1, what you can do is then call this merge function. And right here is where it's taking, so where's the architecture? So right here, I'm taking the output from this layer down here and merging it in with the input that's coming into this layer. And all that takes with Keras is just to keep track of what your variables are named, and then call a merge function like this. So you're telling it to merge this type of layer, the upsampling layer, with a convolutional layer that you saved beforehand, which was saved up here, right? So the point of this isn't to get you to understand how to implement this. The point is that you can look at that architecture and then take it and translate it into like 40 lines of code and get going. And I was actually able to use this code to train a solution that ranked like 25th in the competition. I mean, this is a competition from a few years ago, but the fact that you can do this in under 50 lines of code defining your network, and then to define the optimizer, all I did again was just call compile and tell it the type of optimizer and a learning rate, and then it goes through and it learns to actually segment that image like what I was showing you. So it learns to go from this input to this output. And the final outputs, the way that they look, I'll show you. So these are the results that I submitted to that competition just to figure out how well it was doing. So they're down here. So the titles at the top are small, but the input image is on the left here. The true segmentation mask is this. So this is the one that's given to you by like an expert that's gone through and labeled all this stuff by hand. And then the predicted mask is what's actually coming out of the network after you've trained it. So this is the predicted mask that you're able to come up with given the input on the left. You're getting the thing right here in the third column. And a useful way to compare how well your model is doing in this case was to just plot how many on pixels did you have in your ground truth. So how many of the ground truth were black versus how many were white. That's the histogram on the left side here. And on the right side is what you predicted. So you kind of want to make sure that you're matching the same type of distribution in terms of the classes that you're predicting. So yeah, so the point in all that is to show that you can take a really non-trivial problem that like the world's researchers 3 or 4 years, best researchers in the world threw all their time at this problem, and you can implement it in 50, 60 lines of code that are really easy to read and really clean to go in and make tweaks. Like if I wanted to try all of these with, I don't know, try it with 64 filters right here, then all I would have to do is go in and change the parameter and tell it, try it with 64 filters in the first layer. And that goes back to the point I made earlier about how it's really good for quick, rapid prototyping whenever you're trying different things out for different applications. So yeah, that's it. Does anybody have any questions or anything to go back and look at? Yeah.
That was the functional API right there.
That was the functional, yeah, because you want to be able to like take this conv1 layer and keep it around, and then merge it in all the way up here at this last block that was on the right side. Yeah.
First API you showed us would not have been able to do that.
Right, exactly. You wouldn't have been able to keep that layer around and then feed it into another layer. Yeah, that was the difference. Yeah.
How do you decide on the number of convolutions to use, or is it like?
It's basically unfortunately trial and error. There's no silver bullet to tell you how well to do it. Typically, what you want to do is like figure out what's worked well in the literature. Yeah, that's the best answer I can give. Yeah.
So how long did your experiments take for that?
So on a pretty good GPU, like 12 gigs of memory GPU, it took probably about 4 hours for this to train to where it got to the results that I got in the competition. Yeah. Yeah.
So you showed the diagram that I think from Google that you said worked well.
Yeah, the inception architecture. Yeah.
So is that pure like experimental, or is somebody able to kind of predetermine that could be effective, or is it all experimental?
I'd say it's my interpretation of it is that it's mostly intuition driven. So it's people that have been doing this stuff for decades now, who basically have an idea and then they go and try a bunch of iterations of that idea. And unfortunately, what happens a lot of time is that you end up, I found this thing that works well. Here's me explaining how it works or why it works well, as opposed to vice versa, which would have been, some would argue that here's the theory of why it should work well, and now it works well. Would be better science maybe, but yeah, a lot of it is trial and error driven still for sure. Yeah. Yeah.
Well, no, what was the criteria for the first place or second place in the competition?
For the competition, it's not easy to explain without writing it all out. So the easy thing to do, one really easy thing to do would basically just compute the error in the pixels, right? Like if it should have been white in the first image, but it was black in the other image, then it would, that would contribute to the error. They do a more complicated one that has to do with basically how disjointed the things in the image are versus how disjointed they should be. But whenever you're computing the loss function for this, it's using something called log loss, which is pretty much just comparing the probability, like in any one of these black pixels, the probability of it being black is 1, right? And the probability of it being white is 0. And whenever your network is learning, it's going to output, for each pixel, it's going to output a probability of being white and a probability of being black. And you want to get those probabilities to match as close as you can to what the ground truth is. And so that's what the cost function is operating on while you're learning. Yeah. But then once you submit it, the criteria is very domain specific. So I didn't quite understand what all the criteria was. Yeah.
How is the true mask generated?
By hand.
By hand?
Mm-hmm.
So that's someone looking at it?
Yeah. So these are, it is subjective, but it's typically when you get into things with medical imaging, it's somebody who's, an expert at medical imaging, not at computer science or machine learning. They use some software to draw the masks, and then you try to model whatever they know in their head with the neural network. Yeah. That's basically it. Yeah.
I guess it would be frustrating if you think your predicted is better than the.
Yeah.
Yeah. Well, and it does get really, so sometimes, like with the problem that I'm working on right now, there's different interpretations, really based on the experiment that you're doing. It's also in medical imaging, but based on the experiment that you're doing or what you're interested in, you might label things differently. And so a lot of times we'll take what the experts have labeled and look at it, and look at 2 instances of it and find contradictory labels. So it is difficult, but you do have to deal with that. The sort of the data sets that get used in the literature a lot of times are much cleaner, right? Like it's not that hard to label a 7 versus a 9 or something like that. Yeah. Yeah.
So what kind of practical applications for something like this? I mean, it's incredible that you can do that, in theory and stuff. Like, how would you apply that?
Yeah. So from what I understand, the way that they apply these kinds of things is for basically the people, the biologists researching this or the neurobiologists researching this, to speed up their workflow. That's really the big gain that you get. So another one that's common, that's a common challenge, is doing sort of taking 3D scans from different parts of the body. One of them is like 3D prostate scans and segmenting what part of it is the prostate versus what part isn't. And if you have to have somebody do that manually, then it takes them hours versus training a model to do it in seconds. Then you get a big win in that sense. Yeah.
So the outline of cells tells you what organ you have.
Well, yeah, it tells you. In this problem, I don't remember exactly, but it was valuable to them at the time to be able to just figure out what was a cell and what wasn't, or what was a boundary between cells. Yeah, a big paper that came out back, I think in the fall out of Stanford that got a lot of attention was doing classification of skin lesions for skin cancer. So basically looking at an image, I don't remember all the details, but it was more or less looking at an image of skin and classifying whether there was skin cancer in there or not. So yeah, and that was also using a neural network.
Is it only for image recognition, or do you apply it to like normal data sets as well?
So you can, like I said before, it's typically used for like more highly dimensional data, like text is another one that is used a lot for. Audio is another one that is used for. Language translation is a big one now. But I think what typically happens when you try to apply it to a data set that's sort of tabular, that you have like, you know, a certain measure for a certain category, is it overfits pretty quickly because you don't have enough, you typically don't have enough data. And there's some other problems that arise from that. But people are actually working on that. There was a paper that came out maybe in the last 2 weeks, where they took the UCI data sets. So it's like a big repository of all tabular data, really. And they figured out how to train a network to do really well on all of them. So you can still play around with that kind of stuff. Yeah.
Is there a blog or something that tracks all the new updates in
A good thing to do is follow some people on Twitter. One is Andre Karpathy, and so he'll post. Basically, it's like here. I'll just write them out. Yeah, those are three. Like if you're on social media, you should. I wish I could zoom in on this, but you should look them up. And then there's another big repository of papers called Archive.
But that's so much.
Yeah. So it's really, this is really like it's like a fire hose. Yeah. There's one though there's a site called Archive Sanity. And it's basically a way to filter down archive to find papers that are relevant to what you're working on. So I guess I might be able to log in. It doesn't have enough data about me to predict something, but yeah, if you search like for ISBI, then you would find medical imaging papers. Just because, and it links you back to archives, so that's a good way to do it too. And then sometimes Hacker News is a good one too, but there's a lot of Hacker News, like news.ycombinator.org, or .com is a good one too sometimes.
Those learning resources you posted, can we see those?
Yeah, I'll get them in. I'll make sure to put it up.
Yeah, for sure.
Post it on Meetup first, and then we'll put it up on.
Yeah.
Are you using any of this at Oak Ridge?
Yeah, I'm using Keras actually for the project I'm working on. Yeah, yeah. The project I'm working on is with. Show quick overview. So it's looking at videos that look kind of like this. And so you're taking hundreds to thousands of frames, and you basically have to find where the neurons are. So this is actually like a little slice out of a mouse's brain, and they've used a microscope to image it. And so you want to find where the neurons are. And so in the case of this project, like maybe 15% of the code is the Keras neural network, and the rest of it is sort of pre-processing and getting your data correct and all that kind of stuff. But yeah, Keras is the only thing I've had to use for this so far. Yeah.
So you're using a neural net to find neurons?
Yeah, it's pretty meta. Yeah. Yeah.
And Keras has a whole range of libraries, right? You just talked about the neural net, but.
Well, Keras is specifically for neural networks.
Oh, it is?
Yeah.
Oh, okay.
Yeah, it kind of has, it has all the different types of layers. So but
Okay.
it's specifically for neural networks. Yeah. Whereas something like scikit-learn has all sorts of models in it. Yeah. It's a similar level of abstraction. So yeah, cool. Thanks, everybody.